J'ai compris.
All right. Let's go. Pascal, this time, no introduction. The second talk.
Oh, okay. Good afternoon, everybody. And so today I decided to talk about some recent. I tried to masquer le volet vidéo. No. Yeah, that one. Okay, yeah, compared to yesterday, I decided to switch to some recent interest I had about light matter interactions. So there is absolutely no correlation between what I told you yesterday and today's talk. And so the title of my talk will be about some super-radiant phase transition in solid-state systems. I should put a question mark, actually. And this is a recent work we've been doing with the colleague of the University of Paris, Christophe Morat, and some common postdoc we have been sharing, who is now in Flatiron, New York. You may find more about this work in this paper. Well, what was the context? Initially, I mean, I've been, in the past 10, 15 years, I've been more interested in what we call mesoscopic physics. So transport from nanoscopic systems, and correlation, obviously. And, this field, I mean, scientists have been interested in light-matter interaction for quite centuries now, since the advance of quantum mechanics in the early days. It goes back to the photoelectric effect by Einstein. So this field has been evolved a lot with our understanding of quantum mechanics. It goes back to the 50s with the quantum electrodynamics. And this field got us revolutions in the 90s, 80s, 90s from cold atoms physics. Basically, the gentleman got a very good understanding of the interaction between a few atoms and a few photons at a really, at the ultimate level. They can even see how an atom will decohere in real time by interacting with photons, or the other way around. And so they reach excellent understanding and ultimate accuracy. But then in 2000, people realized that they can actually emulate, mimic this kind of physics, not with real atoms, but with two-level systems, which are described by, as qubits or Josephson qubits, for example, interacting not with a microwave field. So this is the work by the Yale group, by Wallraff and collaborator, this famous paper of Nature 2004, where you have superconducting qubit interacting with the antinodes of the microwave field. So they can simulate atoms in cavity with unprecedented control, full purely electronic system, and they can even go to non-classical states of the electric field and so on and so forth. So now this, many companies are using these technologies for quantum computing at least. And then, the field has been evolving. What happens now, instead of a qubit, you have an open system, like, for example, why not quantum Pi contact interacting with a microwave field? And there are many questions you can raise. What is the properties of the emitted radiation when you pass the current through your QPC? What is the feedback of the electrons, of the electromagnetic mode to the electron, and so on and so forth? For that, you need to reach pretty strong coupling between light and electrons. And that was in the year 2000, 2010. And now people have something else in mind. Well, let's put a real material inside a cavity, or 2D material inside a cavity, and can you change the properties of your electronic material, your electronic systems by light? Can you control them? Obviously, you can, if you irradiate some light, you may excite many excitation in the system and so on and so forth. But could you reach some, for example, some states, equilibrium states, just by light-matter interaction, and can you get some new phase of matter that way? So this is what motivates this piece of work. So before that, I will try to, well, tell you, I mean, I will flash a few papers just to give you flavors about all the questions which are actually raised in the literature. So it's all the amazing things you can achieve with cavity photons interacting with material system. And then I will go through, well, the core of my talk about the superradiant phase transition and some no-go theorem and how to circumvent these no-go theorems. So all the amazing things you can, or perhaps cannot achieve with cavity photons. I will flash a few slides. I mean, at least you may have heard about this work in the Ebbesen group. It's how you typically put molecules inside the cavities, and the idea is that the strong light-matter interactions will eventually control the chemical properties of your system. So you may change the chemical rates of reactions and also the transport properties. You can, if you have a chain of molecules which is insulating, by irradiating them, you eventually can make it conducting. And people, I mean, are now working a lot on that issue. And basically, the idea is that by strong light-matter coupling, you can show that you can, well, induce really modification of the ground state properties of your system. So that's kind of one direction that is actually followed, which is not the one I will. Another thing you can try to do is, can you control the topological properties by light? So for example, in this paper, they consider a sheet of graphene, they put it into cavities with, and they can basically gap the Dirac modes and go from a semi-metal to quantum-one insulators with a perfect quantized Hall conductance. That's a recent theoretical study. That's about, I mean, there are many works in that directions with the idea of altering and controlling the topological properties of your system. Maybe, and that's not quantum light here, you really irradiate your graphene. That's a recent paper by Cavalieri. You strongly irradiate your graphene sheet and you open a gap, and with the idea that, well, eventually it's flow engineering, it's not equilibrium physics. You strongly irradiate it, you restrict very strongly your electron, but you can realize, emulate some, during short time, some kind of a quantum anomalous Hall insulator. Also, the other way around, you can start with a well-established topological phase, for example, the integral quantum Hall effect, and put it in the cavity. And what you will observe actually is exactly the other way around, is that you will destroy the topological property of the system. That's a recent science paper in last March by the ETH Zurich group, where basically they showed that they are slightly destroying the Hall conductance, the Hall plateau, and well, that's so the black curve is the one without irradiations, and the blue one is with irradiation. You better look at the longitudinal conductance, and basically where you have zero resistance here in the black curve, you get some finite resistance, for example, at the one sub plateau, and the same.
How do they rule out that this is just not raising the temperature?
Sorry?
How do they separate this from the effect of just raising the temperature?
That's really obviously something they have to perform this, well, that's a tricky question. Yeah, that's really the things they have to roll out. Also, they have to repeat these experiments again and again to be sure that they are. Yeah, I mean, the typical energy they put in their system is still pretty low compared to the gap. So that's, but yeah, I don't know the details, to be honest. But they have significant deviations from the zero resistance limit. Also, they can, well, I'm not sure you can see, well, they have also significant deviation from the perfect quantizations. Yeah, I don't know, to be honest, how they can do that some eating effect. And here they have in mind the idea, I mean, the theory which is behind, correct or not, I mean, is that the edges are talking via the fluctuation of the cavity fields. So therefore, the two edges are talking, and therefore they slightly hybridize, and that's why they do. That's how they interpret these deviations of perfect conductance. Okay, so that's example of the kind of study people study. Another directions, which is quite appealing, is can you enhance superconductivity with cavities? So they have a bunch of works going on, one by Galitsky group, where they put 2D layer, 2D superconductor inside mirror, and they found they can emulate some Eliasberg enhancement of superconductivity. Well, another more maybe simpler idea is that, well, if you have a strong electron phonon coupling that you can enhance by putting them in a cavity, and therefore it will influence superconductivity. And you can even push the idea by forgetting the phonons, and could you get some superconductivity only mediated by photons? That's a recent proposal where basically the photons are replacing your electrons, and you have a cavity-mediated superconductivity. Obviously, the TC you will get is very, 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 very small. They put numbers which turns out to be wrong, but at the end, we're in the macro-Kelvin version. So, but this is still promising in the sense that you may emulate some superconductivity also by the type of lighter you will. By chiral light and so on, you may induce some non-trivial superconductivity that way and control. So that's one directions you. Well, yeah, it's, we are talking the sub-Kelvin regime, supposed to be when electrons are well screened. That's what I would suspect. I mean, I don't think that's what they assume. It's perfectly screened.
Okay. But what is this funny momentum dependent pairing state? This was not a good old-fashioned Fitzwave state, right?
Yeah, the induced state is a pair density wave.
My brain doesn't remember it.
Okay, but if it's angular momentum.
Yes.
It's not really angular momentum, it's much worse.
Yeah, it's a pair density.
So, I mean,
Right.
Now they can, I think they can, here the induced state is a pair density wave superconductor.
It's a pair density wave, exactly, but of a funny type where there's no natural instability visible to me, which is okay.
Yeah.
Wait, but then how do you define superconductivity?
Like in a pair density wave.
It's a pair density wave, yeah.
Right, so you won translation variant as well.
What was your, sorry? It's a pair density wave, it's a non-trivial to this interaction between light
I was just exhaling.
And but okay, if you already put numbers on that, you have to be careful, and it's really contrary to what they claim at the end. It's very, very small TC. So ferroelectricity that you can enhance. But something I want to spend slightly more time about is equilibrium, so ground state. So there have been a bunch of works, and people have been fighting a lot whether you can, get a non-trivial ground state by putting, for example, graphene in a magnetic field in a cavity. And by non-trivial ground state, I mean, I will let you know, spend more time later, is can you get some photon condensation as a ground state, so what we will call superradiance. And people have been fighting for decades whether such a phase do exist or not. So at some point in this paper, they claim that you can reach at the ultra-strong coupling regime the ground state analogous to the one occurring in the Dicke model with condensation of photon in the ground states. while this paper answered forget it. I mean, actually, well, graphene is still described by, it's not only Dirac fermions, you need to take into account that you have bands and it becomes quadratics. And if you include also the whole band, that won't be the case. And later, following the same logic, I mean, these people, for example, if you start with the quantum spin-hole insulator with Dirac cones, if you irradiate it, you may obtain a Chern insulator with H states. And they claim that so ground state manifold is topological with a Chern number plus or minus 1, and the photon spectral function exhibits a clear bond. That's not what I'm looking for, but there will be some a Dicker type superradiant phase transition occurs at arbitrary weak looping. So there will be the H states will be emit some kind of light. It will be the ground state will be a mix of light electron photon interaction, polaritons like, and there will be some light irradiation, so some kind of spontaneous lasing as soon as you irradiate this phase. Again, this is based on the low energy description of light matter interaction, which takes into account the dispersion relations. I suspect that if you take into account the full band description, most likely you will get different conclusion. Well, and recently there was also another example of such a superradiant non-trivial phase. So that was here was a recent paper by Mazza and George, and here they consider some excitonic insulator. So this is the phase diagram at zero temperature. You have a metal, an insulator, and you have an excitonic insulator in green here. And okay, that's a temperature axis. And they found this phase diagram as soon as you switch on light matter interactions. And they found actually that this excitonic insulator may transform and the phase associated may be enhanced to some kind of super excitonic insulator. That's what the meaning of SX, super excitonic insulator, which would correspond to a spontaneous condensation of excitons and photons in the ground states. Okay, so it's an example, theoretical example, where you will, by light matter interaction, you will, completely change your ground state and get a new phase, which is this super excitonic insulator with a spontaneous condensation of photons and excitons in your system. So, this looks quite exciting. You can really create new phase of matter by light matter interactions. And so that's something which is heavily debated these days, and with a postdoc wanting to go back and examine that in slightly more details. So let me tell you, I go back to history, what is superradiant phase transition, and so my definition of quantum phase transition due to light matter interaction is that at some point, for some critical value of light matter interaction, you get a finite macroscopic number of photons that condensate in the ground state. And this has been found in the simplest model by Dicker in 53. And Dicker considered radiating gas of single quantum mechanical system, so it will be a two-level system, still radiating, so set of dipoles, if you wish. That is described by these polymatrices sigmas. And they interact with a single mode of light. And the interactions is the dipolar light interactions between the electric field and my dipoles. So, and that's the model Dicker has been studied. And what he found actually is that there is a transitions which has been confirmed by exact calculation in the thermodynamic limit. So meaning setting the number of dipoles to infinite and the length to infinite with n over L finite. And indeed, this phase transition was found exactly, and it was found by another different language. And the idea is that, okay, you get You can solve it also by some Holstein-free Markov transform. But for GC equal h bar omega c over 2, you get your polaritonic branch exactly becomes 0. So you have an instability of your vacuum, and you start populating your ground states. So this is what is called superradiance. So you strongly couple light to matter, so here the dipoles, and at some point, for some strong enough coupling of light matter, you populate the vacuum macroscopically. Okay, and that was found for a set of two-level systems interacting with light, a set of dipoles. But very quickly, I mean, after these exact solutions of came this paper, which was, and the idea is that the role of the A squared, and read by yourself, we show that the presence of recently discovered phase transition in Deco model is due entirely to the absence of the A squared term from the interaction of Newtonian. And that was actually the first paper that connects where the absence of transition with the presence of the diamagnetic term. The A squared term is the diamagnetic term. So means if you start with if you install from the very start the diamagnetic term, you don't find these transitions. And that was back in the more than 50 years ago. And well, the natural equations, okay, this was done for a very simple model, dipoles. Can you extend such a study to materials? And you see that it will be, well, you need to go far beyond these Dirac models. Now we have open systems, and well, can you find such a superradiant phase transitions for electronic systems? And if you happen to find it, what are the necessary conditions that you must satisfy?
So can we understand this absence? Is this because the photons interact so strongly then that they just don't want to condense, or what's the upshot of the physics of this no-go theory?
Well, that's my gauge invariance.
Oh, but sure.
Yeah, you want an energetic argument.
Yeah.
Yeah. Here, I mean, the point, I mean, energetically, you will pay the price of A squared term.
So how
it will be
so there would be an A squared term, but how would it couple to the signals? This is obvious. Or is it just?
I think so.
It's just by itself. It doesn't.
Yes. Yes. It's really it's an energetic balance here.
So therefore, the statement is, I don't want to condense because I have to pay.
Yes.
And this is for arbitrarily small coefficient, or is this because, as you say, gauge invariance is a connection between the coefficients?
It's because we have balance.
Thank you.
So let me come to that in slightly more detail. There's been a long controversy about and some no-go theorem, counterexample to the no-go theorem. I mean, to make it short, so you see you have two columns. Many papers have been written on that. So, is it possible to get superradiance with electronic systems at equilibrium? So it's definitely equilibrium phenomena that I have in mind here. And people claim that for cavity QD, there is no way you can get some no-go theorem, but you may find counterexample in circuit QD. Well, the paper I just presented you, they do find a superradiant, superexonic insulating phase, and the paper by Balazsdor also found it. And here they found a route towards superradiant quantum phase transitions, and here is the other column, and then some no-go theorem. And the strategy I will follow today, I will try to drive you through some this no-go theorem based on this recent paper, which is not of mine. So it's a cavity QED of strongly correlated electrons and a no-go theorem for photon condensations. So it's a recent paper, which well, is pretty by yourself. It's maybe not an easy read, but interesting. And this list is far from being exhaustive, and there have been many papers. So here are the two commandments which you may respect and you must respect. As soon as you are dealing with light matter interactions, you must honor gauge in values first. And, you should not neglect any diamagnetic term. So these are the two commandments. And so let's start with a very generic Hamiltonian kinetic term, traction term. And I would assume a single mode cavity field. It's easy to extend to a many mode cavity field. And the idea is to couple light to matter by the minimum principle. So sometimes it's a pi substitutions. The momentum is P minus P8 times E/c. So if you do that, you will get two terms from the kinetic one. That's the parametric term. And you will get the A squared term, which is the diamagnetic term. And now you're, well, that's the Hamiltonian you need to deal with. And you ask whether could there be some phase with a macroscopic number of photons, macroscopic photon condensations. So here's the proof they follow. I'll try to give key elements. There are a few assumptions behind this proof. No relativistic effects, so no spin orbit coupling, all that. And they need to assume, actually they can prove that it's exact in thermodynamic, a separability of the ground state. So the ground state is a tensor product of matter times light. So the first thing you do, you get rid of the diamagnetic term by a Bogomolov transform. So here, notice that all this Hamiltonian is quadratic in the photon field. So you can always do that by a Bogomolov transform, and that's the form of the Hamiltonian you obtain. The price you pay, you modify slightly your light matter interactions by this coefficient lambda, which is related to the diamagnetic. Delta is related to the diamagnetic coefficient, so basically these two factors. And you modify the cavity, you get an effective cavity frequency, which is modified slightly. And then you calculate the parametric current operator, which is just the variation of dH over dA for A0 equals 0. So you get, that's how you get the parametric current operator. And what you want an effective photon Hamiltonian. So you take the average of this Hamiltonian with respect to the matter ground state. And then you're asking, could there be, let's assume there could be photon condensations. So it means a current state of photons. So you will assume that your photonic ground states, you will replace it by a current state. Current state is defined by eigenstate of the annihilation operator here. Fine. And you will calculate your ground state energy of your effective Hamiltonian. So you have taken the expectation with respect to the electronic ground state times some current states, photonic ground states. And it's easy to calculate this ground state energy. And you find you minimize it with respect to beta, and for that you assume it to be a current state. So beta will be basically a C numbers, and you find the value that minimizes your energy. And if you want photons to condense, for that it must be energetically favorable. So you want the energy psi for this specific current state to be smaller than the absence of photons. And if you plug that in, it means that you need to satisfy this inequality. It's a non-trivial inequality because beta bar and psi are still connected to each other. So, in other words, I just rewrite the same inequality as before, and then you use the stiffness theorem, which allows you to write a linear response. So you assume this that the average expectation value of h minus expectation value of h with respect to psi 0 is is in beta squared, and the coefficient is related to the susceptibility, the parametric current susceptibility. So it allows you to if you plug that in, it will have inequalities relating the susceptibility, the parametric current susceptibility to these lambda and beta squared. So if you plug that in, that's the inequality you find. We must satisfy this inequality for photon condensation to occur. So again, this is the parametric current response function in the Lehmann representation that must be larger than the photon condensation, and this is the diamagnetic term. But the point is that you must satisfy gauge invariant to your systems. And if you take a physical system and assume some uniform mode, so the Q equals 0 limit, static, we have already been considering, well, there is no this physical system cannot answer to a change of vector potential, because you can always gauge out the vector potential, so there is no dependence on it. So and this gives you some strong sum rule, which is called a Thomas-Reiche-Kuhn sum rule, or F sum rule. This gauge invariance actually relates the diamagnetic contribution to the constraint, the diamagnetic contribution and the parametric contributions. And this gauge invariance basically tells you that the diamagnetic must compensate the parametric term. So in other words, the parametric term, which is here, must be exactly compensated by the diamagnetic term. And this is a consequence of gauge invariance in your system. And well, if you impose this equality, but gauge invariance impose this equality, then you are back to 0 larger than h bar omega c, which is obviously cannot be satisfied. So therefore, based on these few assumptions, it tells you that gauge invariance excludes photon condensation in a uniform and static electromagnetic cavity field. So omega to 0 and Q to 0 limit. So this phase, all these exotic phases which have been found, at least most of them violate gauge invariance. So, and it's very easy to violate gauge invariance. I mean, you rule about this thing. No. As soon as you take a continuum limit Hamiltonian, like you linearize your spectrum around zero at point, you forget about all the higher bands, and when you do that, you replace P, which is by P minus EA, and you get only linear terms. There is no way you get A squared term. Actually, the A squared terms, if you take the real band into account, there are higher bands, which are quadratics and all that, and the A squared term will be restored. But if you only, let's say, if you project your marker at low energy, switch on light matter interaction and do your stuff, you will get this exotic phase, but they are wrong, because
so one of the assumptions was that these two subspaces were separable. If my ground state of the electronic system, the absence of the light matter interaction was degenerate, so even twofold degenerate, right? Nothing fancy. So then there is a symmetry which I could continuously break, but then I also would expect that the actual ground state would be in some way an entangled state.
Yeah.
Can this help me?
That may help, and this is actually that's one of the assumptions. They assume the ground state to be well defined. Yeah, if the ground state is mainly.
But even doubly degenerate, right?
Yeah.
Not a big deal.
That may, it's a good point. Yeah, that may help you. Will it be enough? I don't think that. I have not seen a proof extending to that direction, but that's a very good point actually. They are trying to. I mean, I discussed with Polini. That's something they are thinking about. I think that the question is open.
Thank you.
Surely a classical electromagnetic field is a kind of complex, right?
Yes.
It's a macroscopic number in some sense. Yes. So I mean that's a proof of principle, it's just a proof of practice. You're not right.
Sorry, what is your point? Sorry, is it related to?
I don't know. I'm just when you have a no-go theorem, it seems to fly in the face of the fact that we physical,
Yeah, here I'm-
static classical electric field. and
Yeah,
magnetic
sure,
field,
but-
right?
So here I mean these no-go theorems, I put some material in a just in a cavity, and there won't be any. I mean, it won't laze for free just by switching on a cookie. That's what it states.
Sure.
So are they? I mean, that's the based on these few assumptions. Okay, this is exact, and that's well. You have to work on the details, but that's not. I mean, it's a linear response and nothing more. I mean, that's it. So obviously the question, can equilibrium superradiance or photon condensations be arise in nature? And I try to convince you, yes, that the answer is positive. And well, that's one option, best way to do 3D metamaterial, the Ivanov singularity. And that's my answer at least, but I will try to drive you through this answer in slightly more details. And well, obviously we need to circumvent this no-go theorem. And this no-go theorem was based on a Q equals 0, purely static. So the most naive way to circumvent the theorem, how about finite Q? So, and a possible route to circumvent this no-go theorem actually was first considered in that recent paper by Pascal and collaborators. And they look at cavity QED for 2D electron gas in the presence of Rausch-Bas spin-orbit coupling in a perpendicular static magnetic field, and they look at Landau level crossings, and they did found some superradiant at finite Q. So we wanted to consider instead of very simple systems, and see whether we can find elementary candidates that would allow for superradiance. So this is the list of questions, and we try to, I think, bring some answers to them. So what is the general criterion to find superradiance with spatially modulated cavity modes? Where and how to guarantee gauge invariance, which is somewhat non-trivial, and characterize the properties of the superradiant phase. And that's these last parts we'd like to spend slightly more time. Let me first answer to the third questions. To avoid problem with gauge invariance, well, we work on the lattice. No low energy Hamiltonian, let's stick on the lattice. And typically, the Hamiltonian I will be considering is lattice, a tight banding Hamiltonian, quadratic, and some eventually I can consider some local density interactions. Okay, that's for the electronic part. How about the light matter interactions? Well, I just do some Pyrus substitutions in the Coulomb gauge. So, meaning I replace my OPIN parameter by address OPIN, and this lambda here becomes just a phase, which is the interval when I hope from RG alpha to RG beta plus, when I hope from position G alpha, orbital alpha, to position G orbital beta plus delta. And that's the potential thing. Okay, so that's what we learned. Quantum mechanics, just Pyrus substitution. So if you expand now your Hamiltonian, you will find a linear term, which is in A, and that will couple to the parity current. And the second term will be the diamagnetic term when you go to second order in the phase expansion. I wrote it in Q space and Fourier space, and that's how there is. So actually on the lattice, the diamagnetic term is quite ugly, but I won't show it. And so you have this electron-photon coupling, which I rewrite here. I will assume a single cavity, finite Q cavity mode, just this mode. And the onset of superradiance would be some ground state instability, so you hope to get some photon condensations for some value of the expectation, for some expectation value of AQ. And again, I will have in mind some current states. So that's what I have in mind. There will be some alpha Q bar with which will signal the onset of superradiance. Okay, you have to work out the algebra, so there are many ways to do it. So you, for example, for this to happen, you need to have the second derivative of the condensate energy with respect to alpha q to be negative. And this, actually, we found after some lengthy calculations using linear response and angle stiffness theorem, we found that this inequality must be satisfied. And here, the key ingredients is the total current susceptibility and the energy of the cavity. Well, I just rewrite it in a way. So first, if you send Q to 0, then you know that, again, the total current susceptibility must be 0 because there is an exact cancellation of the parametric and diametric. So this guy must be 0. And again, you find the same inequality as before, 0 larger than 1, which is not possible. So there is, we recover this no-go theorem, but here which is as expected. And we found something else also in the process. Then we found that actually there is another sum rule, which is called the F sum rule, for the longitudinal susceptibility, which must be 0. So in the directions parallel to the potential vector, to the direction, it means there is no way to get superradiance. So it means that in the 1D system, even interacting as you wish, you won't find any superradiance at finite q, not only at q. So that's an extension of this no-go theorem. There isn't. However, in the transverse directions, we do have room to satisfy this inequality. So let me inspect into this transverse susceptibility. There is two contributions, a parametric contribution, which is negative, and a diamantic contribution, which is positive. And okay, what does it mean? This epsilon mk and epsilon mk plus q is a particle Hall excitations. So this is a dipole matrix element. It's a particle Hall excitations in your system. And ideally, if you want to find some the negative contribution, the parametric contribution to dominate, where compared to the diamantic one, if this term happens to be diverging, then you're in business. So what let's push to the extremes. Let's assume that we have some diverging parametric contributions, and then we know that this inequality will be satisfied. And remember, chi is negative, there is -1 in front of it, then you are sure to find some diverging quantity larger than 1. So if we are looking for conditions to get the diverging parametric contributions, actually, just by inspections, we found that there are actually, we found two ways for this quantity to diverge. First, when we do have some nesting conditions, so when you have two lines of Fermi points connected by finite q is fixed here. However, or to have a diverging density of states at the Fermi points, so kind of Van Hoff singularity. And this will be, we found some, for example, for quadratic or higher band touching. I will show you some example where this term actually give you some log divergence. So let's start with a very simple model with perfect nesting. 2D electron on a square lattice at alpha. Then the Fermi surface is a square. And suppose I will consider a finite q, which connect, for example, the two edges of this square. So a pi, so pi over a, pi over a. Then you can, it's electron on a square lattice, you can exactly calculate your parametric response, and you will find that it's indeed, at the endpoint, it's diverging logarithmically. And so at finite temperature, the log will be cut off, but you find some diverging susceptibility parametric contributions. So in other words, it tells me that below some temperature, Tc, which is unfortunately exponentially small, this term will be diverging and dominating and will lead to the superradiant phase. So Okay, let's forget the numbers, but let's stick on 0 temperature. And so this example tells me that if I go to enough low temperature, I will get a superradiant phase at finite Q. And how could what would be the shape? What would be the properties of such a superradiant phase? So it means now that I decorate my open parameter by some phase. And actually, in the superradiant phase, you will get open parameter which are now phase dependent along some specific directions. And what you realize is that the ground states will acquire a finite occupation number. So you have a spontaneous time reversal symmetry breaking, and you have finite flux now. So the total flux through my well, we double my unit cell, and the total flux will be 0, but you will get a staggered pi flux phase, and this phase now will have some Dirac cones, and you can actually you know what this phase is. You can calculate this. There will be some spontaneous magnetization, which is exactly the one I wrote. So you have it's a staggered flux phase, which was actually studied by some quantum model by Affleck and Marston some long time ago. But here, this spontaneous symmetry breaking realizes naturally a staggered flux phase. And despite I started with a simple tight banding model on a square lattice, and just by the spontaneous flux, I will get non-trivial protected Dirac cones and very natural Berry phase. So, yes.
I'm just probably not following properly, but to get something at such a momentum Q star, don't you have to think about the energy of the photons that having C times Q star, or does it not matter?
First, Q star, I mean, we're talking about pi over A, so you see that it's a huge Q.
Yeah.
So it's pretty unrealistic.
So how are you going to do it?
That's the toy model.
Honestly.
It will come afterward. Yeah, that's on the toy model you can do it, but if you think
you have to have a medium and
yeah, I mean, so yeah,
way down.
So I mean, if you think twice, you see, look, A pi over A, there's no way it will work. So typically, I mean, for sure, light matter interaction does not. I mean, the fact that the vacuum permittivity is a small number does not help you. And what you will need is the typical matter length scale be much larger compared to the typical cavity length scale. So here the matter length scale is the angstrom. The cavity with angstrom, you forget it. So you need this. In my proposal, you will need most likely metamaterials. That to be honest, most realistic. That's what I would. Or I will show you some other example. You need to. Van Hoff singularities might be also promising, you know, but again, still, you will have to face the cavity typical length scale, the transverse cavity length scale, to the typical matter length scale. So you need to make an effective A much larger. Okay, that we can discuss. So that's the second toy model. And electrons on the 2D honeycomb lattice. But it's a toy model, so we are looking for systems with Van Hoff singularities, and we found, I mean, because of colleagues who study that model next door, so we pick up that model. So it's honeycomb lattice, but with third nearest neighbor, T and T3. So that's T3. And we assume that this T3 can be fine-tuned to T over 2, and for this very specific value, actually, you have the Dirac cones now becomes parabolic band touching at K and K prime, so which are sketched here. And what we will consider is that Q will now connect these two parabolic band touching. So again, I'm talking about something of the order of the distance between the two Dirac cones, so it's a very large Q. And for this very specific model, you can show that, so basically nearby you can linearize your spectrum, so it's a particle or excitations. So you replace that by some k squared minus k plus q squared, and you get, it's integral, you will get a log divergency for this integral. And this numerator is finite. So you get, again, a log divergency at the k points, or the k prime. So it means that if you go to, at zero temperature, you have a diverging parametric susceptibility that it needs to be cut off by going to finite temperature. So we know that at zero temperature, this toy model will exhibit some super radiant phase transition at finite Q, and the Q here is the one that connects the two Dirac points. And the funny thing is that, again, let's describe the super radiant phase transition, and you get again a staggered flux phase, which spontaneously breaks time reversal symmetry. So you'll know your Brillouin zone is replaced by your mini Brillouin zone divided by 3 or extended by factor 3 Euro space. And you can check that you have exact, the total flux through the unit cell, the new unit cell is now 0. And what you find that way is a variant of the Haldane model for the super radiant. So here, this is pretty interesting, is that despite you start with something rather, well, you start with a band touching Dirac Hamiltonian with a quadratic band touching, and just by coupling it light, you get some gap opening, and what you found is actually a Chern insulator by light matter interactions. So this Chern insulator, if I diagonalize it on a ribbon geometry, I will find H states here, and these are my H states, which are actually a mix of electrons and photons. And I think that's, well, I found it's a cute example, still completely toy modelish, I agree, where you find an equilibrium topological phase transition by switching on light matter interactions. And this is the, well, you need to go to pretty strong coupling. You can study the properties of these H states and calculate the Chern numbers. And this is the 3 lowest super radiant states with non-zero Chern number. Okay, so that's what I wanted to say concerning toy models. But how about real life? Can I go beyond toy model? And clearly, the ingredient was to have a huge parametric contribution compared to diamantic contributions. Actually, I mean, in a recent paper, Andolina worked out these, after some manipulation of this inequality, they found that actually for 3D cavity, you can rewrite the super radiant criterion in a much simpler form involving what we call the orbital susceptibility. Basically, in 3D, you need the orbital susceptibility to be larger than 1/4 pi. And the orbital susceptibility is the response to some magnetic field, finite Q magnetic field. It's a thermodynamic response. So it means we are looking for materials with a strong orbital susceptibility. That tells you which direction to find. But well, actually, in real life, free fermions they expect diamagnetism and not paramagnetism. So we need some orbital paramagnetism, while in nature, diamagnetism is more common. There are ways out. I mean, people have found it in dot graphene sheets, but and you can find also it in graphene from dia to paramagnetism, but well, still small paramagnetism. This paper plays an important role. Vignale argued only 30 years ago that you may have chance to find orbital paramagnetism provided you look for Van Hoff singularity. We found it by inspection, but it's actually a general criterion to find some, to look for paramagnetism nearby Van Hoff singularity. So that's a calculation we did recently. Actually, and there is a system which is known to to exhibit one of singularities, the twisted bilayer graphene. And at pretty large twist angle, it's 2.8 degrees, for example, we did calculate the orbital susceptibility and found some, well, dominating parametric orbital susceptibility, which is pretty large compared to the spin susceptibility, for example, but still, well, it's dimensionless unit. Remember, I need to be larger than 4 pi, and well, these are very, very, very small numbers, and several orders of magnitude too small to reach super radiance. So even in real material twisted bilayers, you may find it hopeless. I mean, the idea is that here, in this moire pattern, the effective matter length scale is much larger. You can compare to, it's about the Brownian zone is typically, well, 100 times larger than the angstrom, the typical limit cell. But unfortunately, it's very dilute. Still, it's too small to reach a super radiance. So, or maybe some, I mean, in this recent PRL, they advocate crossing between Landau levels. But if you look at the superior instability, it does exist. But if you look at numbers now, they found it. You need an extreme fine-tuning of your magnetic field up to 4 digits. It's 0.1237, 0.1237, so 5 or 10, 6 digits of fine-tuning. So there is no way you can reach too much fine-tuning, whatever disorder will kill it. So it looks a bit disappointing. I mean, this phase does exist, this phase, but demands huge fine-tuning. So well, I think maybe metamaterials offer one way out, and with that, I would like to summarize. So at least this superagent instability takes place at finite wave vector. It does exist, but unfortunately, the coupling is very small, and the conditions for it to be reachable, you need matter to match this 1/2. And for realistic cavity, which is a transverse cavity, cavity is something physical. It has at least a micrometer or maybe 100 nanometers typical size. Well, that's really metamaterials, I think. Otherwise, pretty much hopeless. And I repeat, okay, that's a bad copy paste. So that's my message. There was something else I wanted to. So, and with that, I would like to conclude. And let's hope for metamaterials and superradiance with genuine materials seems still dream today. We need a very good idea. Thank you for your attention.
About the high-flex lattice, in my understanding, don't actually break down versus flex plus pi minus pi.
Yeah, but still, you have no total flux is 0, but still you have some. It's like the Aldane phase. You do break down versus.
Right, but I mean, it's a bit academic to say whether the flex is positive to pi or negative pi.
Yeah, but it's an alternation here.
You can always insert integer flex. It's just a gauge transform. Now the question is, are you allowed to gauge transforms here, or not? I mean, you know that on the real Hamiltonian.
Yeah, but we need right. It's not a total. It's a non-uniform gauge transform, and it's alternating flux. So pi minus alternating. It's like in the Aldane phase. It's a pi flux phase. It's called in the literature.
So I mean, the question is, are you sensitive to the gauge in all space, not just in the lattice positions, to the degree that those two things are distinct? But as far as the lattice is concerned, the two are actually the same. But if you start from pi substitution, then you can only define flexibility with pi with pi substitution. So those two things are actually second pi flex analysis equal to induced flex.
I don't think I agree. I cannot gauge away this staggered.
Unless you have a continuum like the potential in continuous space. You only consider on the lattice.
You can take it away. You can put it at the border, maybe, or
No, I mean, you can write down Hamiltonian, which is real, and which has a vector spectrum.
but the thing is that 5 flux phase is equivalent to no phase at all, which
No, that's not true. No, you double the units. You can't distinguish both the units. It doesn't break. Might have.
Same as 90 for magnets.
Yeah, it breaks.
No, you have to translate by one.
If it goes to nodes. Yeah, I mean, we probably distribute space symmetrically to all four links. I'm not going to do that. We put it on just one link. Except that
here that the
linear calculations are continuous variable and
No, it's not. Working the lattice, there is a finite q pi pi, so this pi pi require, and this direction is in. That's it. Yeah. I'm not convinced.
Written down the Hamiltonian 5 flux lattice.
This is dispersion relation. There's no way to do it.
Well, I mean, the thing is, the dispersion relationship depends on the gauge.
Yeah.
So you can just map this dispersion relationship to select different shapes.
And the key here that I do get is Dirac terms which are very protected.
Yeah, no, the Dirac ones, they're there.
There's no way out.
Right.
And so you'd be claiming there would be no spontaneous currents for magnetization.
Well, that's not.
The total magnetization is 0. That is fine.
And the current.
I know. Yeah. I've been my loop currents.
That's true. Yeah, the statement rate, the Hamiltonian.
No, I've loop currents. I mean, inside plus. If you consider this loop, it's 0. And I can.
All right. Yeah. Say the expectation value here are influenced.
Exactly. That's my statement.
What would happen if you put something like a quasi crystal in the cavity that is somehow could be a problem, or can you say?
I can let you answer to the question.
Or how is the periodicity important except for simplifying the problem inside this?
I mean, here we reach this super. I mean, because with this, in that case, we're nesting. So I mean, basically, the many processes which connect to and I would say that this works the other way around. Because the crystal is no open to different surfaces. There could be dilute and no way.
Yeah,
I would say that.
argument.
So it's. I think it will be a diametric response that will dominate. But I don't know what is the orbital susceptibility of the principal
Yeah,
space.
exactly.
I suspect to be diamagnetic, mainly. No. But I mean, if you want to retain something, low energy resonance, I mean, if you're interested in light matter interaction, many people are, go under gauge environments. Because working with low energy resonance, you like to do a switch, I mean, white light matter coupling is dangerous fix. Because you start with something that violates gauge environments, and you may find all the crazy things you like that are trustworthy. And so it means we raise a few issues. If you want to, for example, I mean, there is the idea these days to combine DFT band structure and incorporating light matter coupling at the heart of DFT. It's not so easy. I mean, how you make sure that you guarantee gauge environments? That's not easy. At least the proposal we would like to follow is, okay, do the DFT calculation with light matter, we find the Vanier web functions, we go on the lattice, and then we switch on light matter coupling. Is it equivalent to finding a way of incorporating light matter interaction at the level of DFT? Do we find the same physics? I don't know. This is a pretty open question. And this issue about gauge environment, all that is not only crucial for this exotic phase, but if you want to, I don't know, look at finding enhancements of superconductivity, all that, that's something we really need to be careful about. Especially if you want to go to strong light matter coupling. So I see that.
If I go into a superconductor where the photon gets a mass, can I then avoid all of this trouble?
What are you referring to?
Huh?
Difficulty with gauge invariance?
Yes. Well, let me rephrase it. I go into a material with a highly singular dielectric function.
Yes.
Which is maybe a more mild way of saying something.
Yeah.
And so therefore, my actual photon propagator, because it sits in a complicated environment, maybe this is so general that you can't get away from it, but here the photons are always taken as God-given and untouched. But we do know in many materials they do change the property significantly. And the photon propagator, while preserving gauge invariance, looks very, very different from the single mode description that we do. Is there any way to get back into the game? And superconductor is just the craziest version of it.
Yeah.
Isn't that,
That's the thing. That's correct.
and I've heard that most of the main advances in the area of photonics are you're not really dealing with, you say, dealing with metal material, you're not dealing with electronic material per se. But then, of course, you don't have fermions in the same sense. The photons in general. Now, the interaction with quantum fluids. Isn't the fact that the sea is so extraordinarily large that something in practice means you have to think about something where the energy scales and wavelengths are more ideally matched?
Exactly. That's what metamaterial might be the only way to do this.
To rephrase the statement, I mean, I think there's some connection between these comments. I mean, suppose I am in a metamaterial, my artificial pattern couples to the light in some subtle way that we don't even want to understand. But it does look very different from the minimal coupling that we do when we couple to the naked electron, which is nothing else but saying that's a complicated dielectric function.
Exactly.
Right?
That's I think that's where I would more or less re-explore. What I learned from that is the conventional way, let's forget it. And if you put numbers, really you are out by orders. So I would explore more on the material level.
Right.
Cavity, look, we do know cavity with 1 micron thickness, maybe even less. You won't never do an unstreamed cavity. So the only way to work around the material and look at non-trivial, yes, I fully agree. So for this community, forget superradiance. However, well, still, we may manipulate a little bit, and these days, people on some huge enhancement of superconductivity. You are far from equilibrium. You already send a laser to you almost destroy the sample, so God knows what you are doing. Check your electrons so plastically. So it's far from an equilibrium well behaved medium. I can understand that to be ready to system for every year, you may enhance some specific funnels and therefore enhance the TC. So that is cavity funnel engineering might be an interesting way to at least manipulate the superconductivity picture all the direct. That's something which is, I think we see more progress in the years to come. Wow. The heat wave also is in London.
Isn't a semiconductor laser in some sense an example of something where you've got a coherent combination of an electronic medium and the electromagnetic medium? You've got a continuously operating solid state laser. That surely is an example of a coherent state of radiation coexisting and interacting very strongly with the fermionic system, which is driven. Another example of in a cavity, you can keep it there, you can boost its intensity. So I guess I wasn't really sure from the beginning what super radiance really meant, actually, whether that was.
Super is equilibrium for synchronization, not driven. Relays for free. To be clear, I mean, super radiance has never been observed. So 30 for the moment, just observed in phase. And but driven, okay.
What was the difference between that and the subject of time resistance we heard about recently? Isn't it really the same thing? It's not static.
Yeah.
Then it's the version of the time crystal. It is static, just static electric and magnetic fields.
Yes.
Can happen. Right, so you would call that super radiant. So isn't the super radiant state in where you define really example time crystal? A ground state which spontaneously breaks time. Yes. Time translation. Or was it supposed to be a state that didn't break time? macroscopic field that was varying with time, it would be an example of a time crystal. So it's subject to all of the no-go theorems that were advanced there too.
Yeah, I was in omega to 0 limit, so
Oh,
your time crystal will escape that.
you don't want to be omega equal to it, or you do.
No, the proof I provide was omega equals 0. So if you allow omega finite, then
But omega equal to 0 is it's a static electric field, you know? But every crystal has got static electric, spontaneously formed static electric fields.
The photons itself finite frequency.
But
But the expectation
Expectation
of
value.
that system then is supposed to be time independent.
yes, that's what I meant. So your time crystal, this is beyond that. I have nothing to say in the sense that it could be some kind of super radiant and time to time super radiant. There is no noble theorem for that. That's my mistake.
As we are just educating all ourselves, and I'm teaching statistical mechanics, I tell students always that photons don't condensate. Or maybe they do, but why do I care? Because this would be zero energy, and if there isn't any particle of zero energy, you have to be hell. It's just a mute discussion. Now, can you just summarize one more time for us what's so qualitatively different in a cavity that we can go to condensate? Because there's always a statement, oh, the photon is an antiparticle, and that way I can create many of the wishes, zero energy, and therefore I can condensate in the lowest state, right? That's the usual words that we all use when we do this. Is there anything that which aspect of these statements is now wrong?
So, the point is not really the situation are trace. So my basic entities are trace selection photon interactions. So,
Yeah, the statement is if
Yeah, the macroscopic
photons were to
occupation-
condensate, they would do so at zero energy, that's the lowest state. But I can get without any penalty a zero energy particle hole excitation that produce me 16 photons or 9, so there was no convention.
Macroscopic number.
The whole discussion makes no sense, right? You're saying the cavity energy is finite. I think this is something important here. But,
I think there's something like that.
Yeah.
In that, there's also that constant dimensions to get zero energy, and then in the cavity, it's got so I think there's something to do with the cavity being finite energy that means that sometimes it should be. But like there's all this stuff about baritone condensation. These things come up there. So what sort of radiance is what is
Yeah. Actually, definition of superradiance is very confusing from one place to the other. I don't think there is. Yeah. Mine is on the macroscope and macroscopic occupation on the vacuum. But superradiance is a word which is used by many people for different things. And makes the whole literature very confusing. So that does not help, but this, yeah. If you see the word superradiance, you have some You need some alarm. What does he mean? That's not always the same thing.
Just curious why the notion of being in a ground state was inserted into the definition. I mean, definitions, you choose definitions to be useful. And so, what was the motivation for introducing the requirement of in the ground state?
Could it be beyond 0 temperature?
Historically, the whole formalism of coherent states was developed for photons.
Yes, true.
So, which we of course use to describe the condensation of photons every day.
Yes.
And you use particles, Savre points, everything else. So definitely the concept that was developed in the context of photons is used there in an everyday context by theoretical physicists doing condensed matter physics. And the entire setup of particles relies on Glauber's coherent states, which were inspired by photons. Yes. So we have no question that photons can condense into coherent states. Yeah.
Used for massless photons.
Yeah. Interesting discussion. Any final points? Great. Good discussion. Prompted a lot of changes of action. Right, so now
Yeah. Share screen.